In single-variable calculus, the derivative is a slope on a 2D Cartesian graph. We see exactly how y changes relative to x along a one-dimensional line. Complex numbers like z equals x plus iy present a visualization crisis. Because the input and the output are both 2D points on a plane, a standard graph of a complex function would require 4 dimensions. We solve this by visualizing a machine transporting points between two distinct 2D maps, the input z-plane and output w-plane. A complex function w equals f of z takes an input vector from the z-plane, assigning it to a new position in the w-plane. Mapping the transformation of w equals z squared reveals the geometric mechanics of the complex derivative. By tracing these movements, we can count the roots of polynomials through visual observation. This transition from static algebraic equations to geometric arrow mappings exposes the topological structure of complex calculus. We can map these mechanics by examining the function w equals z squared. Cartesian coordinates make the geometry of multiplication difficult to see. To track how squaring affects a point, we convert z into its polar form, r, the distance from the origin, and theta, the angle. Squaring this polar coordinate yields r squared times e to the power of I times 2 theta. This establishes a rule: square the distance and double the angle. As a z-plane vector sweeps a 180-degree semicircle, the corresponding w-plane vector doubles that rotation, tracing a full 360-degree circle. This rule warps straight input lines into parabolas. Because the distance r is squared, points further from the origin grow at a faster rate than those closer to the center. Complex functions dynamically fold, stretch, and wrap mathematical space over itself. If a function like z squared warps a straight grid into a curved one, how do we define a derivative or a slope at a specific point? We look at a tiny movement in the z-plane, h. The resulting change in the w-plane is found by multiplying h by the derivative, f prime of z. Complex multiplication always results in a simultaneous scaling and rotation. The derivative f prime of z takes that tiny input arrow h, stretches it by its magnitude, and rotates it by its angle. In this microscopic view of the z-plane, we see a square with 4 perfect 90-degree angles. When this area is mapped to the w-plane, the square rotates and scales, but it retains its 90-degree internal angles. This property is called conformal mapping. Complex differentiable functions preserve all local microscopic angles, despite the large-scale distortion of the grid. The complex derivative is a local preservation engine. It ensures that the microscopic geometry stays locked in place through a uniform scaling and rotation. Achieving this level of angle preservation requires a specific algebraic balance. We break the complex function w into its real part, u, and its imaginary part, v. For the derivative to have one definite geometric value, the result must be the same whether we approach a point horizontally or vertically. This requirement links the two functions through the Cauchy-Riemann equations. The partial derivative of u with respect to x must match the partial of v with respect to y, and the partial of u with respect to y must be the negative of the partial of v with respect to x. The Cauchy-Riemann equations act as a rigid compatibility rule. If the real and imaginary functions do not satisfy this exact relationship, the local scaling and rotation fall out of sync, destroying the conformal property of the mapping. Complex differentiable functions require their underlying components to be perfectly aligned to maintain geometric consistency. Conformal mapping works at every point except where the derivative is 0 or infinite. Consider the case where f prime of z equals 0. Because the local stretch factor is 0, the tiny input arrow is crushed. The angle-preserving geometry collapses. At these points, higher-order derivatives take over. Space folds over itself, similar to the doubling seen at the origin of z squared, and the local rotation is lost. These zones where the local geometry fails are the algebraic roots of the polynomial. We can use these geometry failures to find the roots of a polynomial without performing tedious algebraic calculations. A polynomial can be viewed as a series of factored vectors multiplying together, a times z minus c1 times z minus c2, and so on. We perform a geometric test, moving z in a closed loop in the z-plane, producing a corresponding w-plane path. If the loop contains a root, the output vector makes a full 360-degree rotation around the origin. If the root lies outside, the behavior changes. the vector swings out and returns to its original angle, resulting in a net angle change of 0. The global path of a complex function is determined by whether or not it swallows a root in the input space. Since a polynomial's total angle is the sum of the angles of its factors, we can count roots by observing how many times the function winds around the origin. This is the argument principle. The total change in angle divided by 2 pi equals the exact number of roots enclosed by the input path. Solving high-degree polynomials algebraically is a difficult process of blind calculation. The geometric approach allows us to verify the existence of roots by watching how a function forces mathematical space to rotate. Mapping these dynamic, moving arrows exposes the topological structure at the center of the complex plane.